Have you heard about the evil bit before? Did you know that it still exists in Internet Protocol packets? I'm not kidding. There is a bit called the evil bit that you can set to 1 or 0 whenever you send an IPv4 packet, which is basically every time you access the internet. Hello Internet, this is Arya, and today I'll be detailing what every single field in an IPv4 packet header is responsible for, and different ways that they can be exploited. I'll also be sharing with you some fun facts about the IPv4 packet, like the evil bit, somewhere in this video. This video will focus on the details of the IPv4 packet and is certainly not worded for beginners. I did briefly describe the most useful protocols in the previous video about IPv4. This video will go into so much more detail. This is useful if you're looking to design your own protocol, write a protocol on top of IPv4, or have a deep understanding of cybersecurity. After watching this video, you should be able to construct your own IPv4 packets with hand, from scratch, since you will know what every single bit is responsible for. So let's get started. Our first field is the version field. The version field takes 4 bits, so it supports numbers from 0 to 15. For 0, we have IPv0. It was used in the beginning days of the internet, back when it was exclusively used by the US military. IPv1 to IPv3. Before the IPv4, obviously, these protocols were getting tested, but they never reached the public. IPv4 is the one that everyone uses today and was the first internet protocol that reached the general public, and is the same version of the internet protocol that we are talking about here. IPv5, or the stream IP datagram mode, was an upgrade to IPv4. It used the same IP address structure and had many similar traits. IPv5 mainly focused on streaming video over the internet. It was also commonly known as ST, or the streaming protocol. This protocol eventually became the basis of voice over IP. IPv6, an amazing protocol that will be the future of the internet as we know it today. It supports much more internet users and would be more efficient in getting the packets across. The header size, for instance, is a fixed 40 bytes instead of 20 to 60 in IPv4. That is very impressive, considering that IPv6 addresses are 4 times as large as IPv4 addresses. So the source and destination addresses on their own account for 32 bytes of these 40 bytes. IPv7, or the TPIX, was another experimental protocol that became obsolete. Fun fact, it came before IPv6. The only reason why it has the number 7 was because the developer mistakenly assumed another protocol was going to use number 6. So then IPv6 came, and they decided to use number 6 as it was the smallest free version after 4. IPv8, or the P protocol, or the PIP protocol, was another protocol that was proposed in the 90s. As of now, this is also obsolete. Some ideas from the IPv8 found their way to SIP, which was then merged into IPv6. IPv9, Tuba. Tuba was designed to deliver TCP and UDP over bigger addresses. This protocol is also obsolete. IPv9, China. China started working on IPv9, which worked with 256-bit addresses. This is double the size of IPv6 addresses, much more than we probably will ever need. This was a waste of time and resources. IPv6 already has enough addresses to give every star in the universe 4.3 billion unique IP addresses. So chances of us colonizing all the stars in the universe and not coming up with anything better than the internet, as we know it today, are pretty slim. So the Chinese IPv9 was just a fantasy and a waste of resources. That is why they abandoned it, so this protocol will also never see the light of day. IPv9 was published in an internet memo on April 1st, 1994. As you might have guessed, this was an April Fool's joke. This memo talked about how viruses were making IPv9 chips via genetic mutation. Really crazy stuff. Honestly, I feel like there is someone that actually believes everything IPv9 said as a joke somewhere in the world. IHL, or internal header length. Then we have the internal header length field, which is 4 bits long. This field contains the length of the header measured in 32-bit words. A header can be 5 words minimum and 15 words maximum. In bytes, that is 20 to 60 bytes long. DSCP, or differentiated service code point. This field was originally called the type of service or TOS. This field helps the network admins prioritize specific types of traffic. So for example, time-intensive traffic like online gaming, voice over IP, and video conferencing could be delivered fast, and some packets that prefer reliability could be handled with more care. ECN or explicit congestion notification. This field basically tells the sender to send packets at a lower rate. When there is a lot of load on any router along the way, using these 2 bits, the router signals the client to slow down. This field is critically important if you're performing an educated DDoS attack. This way you can understand if a router along the way is getting DOSed instead of the target. Of course, the target itself can set this value too, but in case you're receiving congestion signal from only a couple of paths and not all your requests, you can direct signals away from the congested router using proxies, etc. and then hit the target again, potentially at a higher rate since the congested router is not slowing the request down anymore. Also, if you continue, you might DOS part of your own ISP. Then you will lose coverage and won't be able to carry out the attack, at least for a short period of time. If you're receiving congestion signal from your target, the signal translates to go harder because the server is going down. Of course, I'm not advising you to perform DDoS attacks on anyone, and this is only if you're testing your own infrastructure to make sure they can withstand DDoS attacks. Total length. This 16-bit field defines the entire packet size in bytes, including the header and the data. So the minimum size is 20 bytes, which is the minimum length of a header, and the maximum size is 2 in the power of 16. Identification. Since the IP packets can be fragmented at the host or the routers along the way, and will only be reassembled at the destination address, this field identifies a group of fragmented IP addresses so the destination could put them back together. Flags. The flags on an IPv4 packet help the routers understand if the data can be fragmented or not. This field takes 3 bits. Fun fact, IPv6 does not allow data to be fragmented by the routers along the way, as data fragmentation sometimes causes problems. The first of the 3 bits is called the evil bit. This bit was an April Fool's joke to poke fun at some ideas that might sound good as an idea, but have zero practicality. This bit basically asks the attackers or anyone with bad intent to set this bit to 1. This way the firewalls, the networks, and everything would be extremely optimized since they would just drop all the packets with evil bit equal to 1. Obviously this is just a joke, and no one is naive enough to think that our black hat friends would actually be honest about their evil intentions. The second of the 3rd bits is called the DF field. This field tells the routers along the way not to fragment the data any further. DF, don't fragment. This way, if the router cannot pass data through, it would just drop it. The last bit, which is also called the MF bit, tells the server that more fragments are coming. MF, more fragments. You have to understand that different fragments arrive at different times, so this bit will tell the server that this fragment contains the ending of the packet. So everything else that arrives will be put before this fragment at their correct spot. Without this bit, the server would not know if all the fragments have arrived or not. Mail example. Imagine you're sending pages of a random text to your friend, each in a parcel in the mail. These mails might arrive at different orders. So the last one might arrive first, and then the 3rd one, then the first one, or any other random order. So you have to also provide a page number. But how is your friend supposed to know if all the pages have arrived? Let's say page 1 arrives. Should he wait for the 2nd page or not? Well, one solution would be to provide a total data length field. This would be more expensive as now a larger packet has to be transported every time. Let's say we measure the data size in bytes. To send a 10 gigabyte file across, we need 24 bits of extra data with every request, which is completely unreasonable. Moreover, if you don't know the size of the data from the start, let's say in a voice call, you don't know if the call is going to be ended in just 5 minutes or an hour. It is much more efficient to have a bit indicating that this is the last fragment, and as soon as all other fragments in between arrive, the packet has officially arrived and can be processed. Fragment offset. This field tells the server where to put this fragment relative to the start of the packet. If there are no fragments and this packet is intact from start to finish, then this value would be 0. This field has tons of exploiting opportunities associated with it. Buffer overflow, overlapping fragments, and so on can really bring a server down or give the hacker a way through if the server has vulnerable code. This is like the page number on the pages sent through the mail. It will tell the receiver how to organize the frames. Time to live. The time to live field, which is also known as hop limit, limits the number of routers a packet can pass through before reaching the target. So every router your request goes through reduces this number by 1. If the number is 0, the packet just gets discarded. This is just to prevent network loops where a packet goes in a circle, never reaches the target, and just puts a constant load on the network. Without the time to live field, these packets that get stuck could pile up and eventually DOS the entire network, or at least parts of the network. The protocol field tells the server what protocol this internet packet uses inside. For example, it could be TCP or UDP. There are many protocols, and IANA's website contains a list of them with their binary representatives. As always, you can find the link down in the description. This field is super important since if the attacker does not have the resources to attack TLS and HTTPS, which most hackers don't, they can filter all the insecure connections over HTTP and perform their attack. Header checksum. The header checksum holds a 16-bit value that is calculated from the header. So if the data is corrupted along the way, this checksum won't match. Every router has to calculate this checksum once to see if the packet is valid, then decrease the time to live and recompute the checksum again, and then send it to the next router. And at last, the source and destination fields are the two most important fields of an IPv4 packet. The source IP address is where the packet initially came from, and the destination is where the packet is hoping to end up. Please note that the source address does not change from start to finish unless there is a VPN, proxy server, or a man-in-the-middle attack at work. The source field is vital to us since in DDoS attacks you would randomize the source IP address to get past the firewalls and spoof your IP address. Moreover, people that don't want to get detected, whether they are cyber criminals or whistleblowers or even important individuals like politicians, they have to make sure that no one knows where they're going. So they send their data to one, if not multiple, VPN servers, Tor nodes, and proxy servers. Then the last node in their proxy chain would send the data to the website. And through a similar path, the response ends up coming back to them. This way, if the ISP or a hacker or anyone else is listening to the connection, they cannot see who is connecting to which website, and your connection stays completely secure. Options. Options are the last fields. They are mainly used for testing, debugging, security purposes. If the options is not a multiply of 32 bits, padding will also be added. Thanks for watching this video. I hope you enjoyed it. I have links to articles and videos on the topics mentioned above in the description. You can access my posts and pieces from my personal website or my YouTube channel. So definitely take advantage of those resources. So until next time, stay paranoid, stay alive.